Good afternoon, CS109. How are you guys doing today? Oh, fantastic. That's what I love to hear. And the word of the day is Happy Wednesday. I hope you guys are having a fantastic day. I know we're at that midpoint of the quarter when lots of things start to get a little bit more intense, and I just appreciate you guys for doing what you do. And one of the ways of showing that appreciation is we've got a very fun class today. We're going to learn something incredibly useful, and also which is expansive. It takes the things that you've started to learn in CS109, and it's going to allow it to expand to describe more and more complexities in the world. We are going to be learning about probabilistic modeling. So thinking not just about one random variable, not just about two random variables, but a whole bunch of random variables being random together, maybe like a real world scenario. You will walk out of today's class hopefully having mastered or understood some of these core techniques for modeling. Okay. Then I also have a little bit of a hook for you. I want to tell you about one project that I found very interesting. One of the things that I found very interesting, especially when I was a PhD student, is that computers were so bad at understanding beginner programmers and the mistakes that they would make. So to give you an example, there is this website called code.org, and people write programs using these very simple block-based languages. Their programs are like 6 lines long. And computers were a total disaster at looking at those 6 lines and understanding what misconceptions the student has. Like, you look at this block of code and be able to say what sort of idea the student was missing. And code.org has a lot of data. They have tens of thousands of students, and 37,000 unique solutions to this 5-line program. They have lots of history. They can have some teachers helping with this process, and yet they were not able to understand basic mistakes that students make. I'm going to jump to the conclusion, but to understand how we got to that conclusion, you'll have to follow along today's class. So the idea that we came up with was, well, first, can we just use some pretty basic statistics, like count conditional probabilities of mistakes given the fact that they have a for loop, or given the fact that they have an if statement in the for loop? And basic statistics didn't get us very far. You might have heard of this exciting thing called deep learning, and we tried a lot of deep learning on this. And if green is how well humans do, and you want to be high on this chart, deep learning wasn't getting very close at all. But we took some inspiration from this beautiful project which described a probabilistic model over all the ways that humans could write hand-drawn digits or characters. So for this particular character, you can create a whole probabilistic model that describes the process that somebody goes to write these characters. We took inspiration from this, and we brought it to the world of beginners writing code. And we thought, well, what if we wrote the probabilistic model for beginners writing code? And we did, and it was a good time. And by we, I mostly mean there was a student called who was a TA for 109 a year ago. He wrote this beautiful generative model, and it was able to outperform humans at the task of figuring out what bugs a student had. Now, code is a complicated thing. Think about imagining code in the world of random variables. And by code, I mean like the whole production that a student makes. It's a complicated thing. There's lots of moving pieces there. You're going to need something more than just one random variable. You'll need something more than 2 random variables. Stick around for today's class, and we'll talk about how we can get to many random variables. But let's build a foundation of where we left off first. This whole section of CS109, probabilistic models, comes down to talking about random variables being random together. If you can have a deep understanding of random variables being random together, you're in a good place. And the most important fundamental concept in this world of probabilistic models is this idea of a joint distribution. A joint distribution says, if you have 2 random variables, can you give me a function, an equation, a piece of code, a table, anything where for any assignment to all my random variables together, you can tell me the probability of that joint assignment. The joint is the be-all, end-all. If somebody gives you a joint, they've given you complete information about the probabilistic model. Please do interrupt me if you have questions or anything confusing about this. It's a good time to talk about it. Okay, I'm seeing some thumbs up, which makes me feel good. Now, if the joint was the most important thing you wanted to have, the most important question was the question of inference. And the question of inference says you observe some random variable, and your belief about the other random variables may change. We've seen inference in many forms. One inference task that we saw at the beginning was you would look at the weight of an elephant, and we would just infer an updated belief about the gender of the elephant. This was a very simple model where we imagine the gender of an elephant was changing the distribution of their weights. So if you observe weight, you could infer a little bit of signal about what gender they were. It's not a very practical problem. No one's like trying to gender an elephant by weighing them. That's a silly thing to do. But a less silly thing to do is what we did in last Monday's class. In last Monday's class, we did this harder task, but much more meaningful task of doing the visual acuity inference. And just a second while the HDMI catches up. In the elephant task, you were inferring a Bernoulli. It could only take on 2 values, so you only had to do one Bayes' theorem in order to update your belief. But on Monday's class, we inferred a random variable which wasn't Bernoulli. In fact, it was a random variable that was represented using a dictionary that took on way more than 2 values. It could take up 100 values. And when you did inference, you had to update your belief that the random variable took on any of those random variables. So you didn't just need one Bayes' theorem, you needed a whole for loop of Bayes' theorem. So that was the big upgrade that we did last Monday. And also, I just want to point out quickly that in Monday's class, we did this really cool computer science thing where we represented this random variable using a dictionary. And that dictionary could map different assignments to the random variable to the corresponding probability. So you can think of the whole dictionary as the random variable, and a single look, or like, a key would be like the little a, and a lookup would give you a probability. And for those of you guys who are more used to computer science, maybe this is a nice little metaphor for random variables. Yes?
So to clarify, the reason why we didn't use Bernoulli in, in the second example is because we didn't know that there's just like a 100% chance, 0% chance it's a girl or a boy. We had to have a function to describe hearing and not hearing. Is that?
Oh, yeah, going back to the first example, the elephant one. So in this world, you would observe weight, which is a very continuous thing, but the thing we were inferring was the gender of an elephant, and that's Bernoulli, because it could only take on 2 values. I mean, what a heteronormative way of looking at elephants, but that's what we did. But it was Bernoulli because in our world of gender, there was only 2 values.
But isn't there only 2 world of values, like hearing and not hearing? Isn't that one?
Oh, and for this visual acuity, you mean? Yeah. So seeing or not seeing? No, there's way more detail to seeing. Like some people can see 20/20, so like you can see without glasses at 20 feet, healthy vision. And my vision in my left eye is 2100, which means like 5 times worse than an average person. So there's a whole shade of gray between you're seeing like a healthy adult versus you can't see anything, and there's all these shades of gray, and we want to keep beliefs about all those shades of gray. In fact, in order to say how well somebody can see, you really do need to do that. You need to keep track of all the nuance. Random variables and beliefs. Oh my God, you can express yourself so much better once you master this idea. It is such a powerful language that the whole world doesn't seem to speak, but now you guys will now know how to speak. Okay, so this was our big upgrade, going from inferring a Bernoulli random variable to one which could take on 100 different values. And that required us to do Bayes' theorem 100 times, but we had computers, so it was kind of fun. Number of dictionary, I've mentioned this a little bit. And then I wanted to point out 2 things. What are these terms? This term was your prior. This term was how likely was an observation given the true state of ability to see, which was a knowable thing. And based on these 2 knowable things, we were calculating this hard to know thing, the updated posterior of ability to see's inference. Now, this was kind of crazy. When you look at code for people who do Bayes' theorem on random variables that can take on more than 2 values, you often see code that looks like this. You often see code where you see references to things like the prior. You often see code that has references to things like the likelihood. But you hardly ever see code where they actually, in the inner for loop, where you expect that they would be calculating the probability of y equals 0, you hardly ever see people actually calculate probability of y equals 0. And instead what they do is they calculate all the numerators and then they normalize them. What an insane thing to do. So when you actually look at code, people don't calculate probability y equals 0. Instead, they calculate all the numerators and normalize. The reason that works, if you took probability y equals 0, if you expand it using the law of total probability, It basically says, okay, we're going to loop over a again, and for every possible value of a, we're going to take one of these numerator expressions. The probability that y equals 0 given that a equals each of the indices in my for loop times the prior of each of my indices in the for loop. That's the thing that we were calculating in the numerator every time through the for loop. So basically, this normalization is a really, really nice, neat trick to skip having to calculate this and then just realizing that you can calculate all the numerators, and then if you normalize it, it will implicitly give you all this calculation for free, because normalization will do the sum over this, that gets you this term, and then it's going to divide every term by that sum. Wow. Do I care that you can use the normalization, this really shorter version of code? Not so much. Do I care that you know Bayes' theorem expanded? Yes. But do I think that you need to know that these two things are equivalent? Absolutely, because you're going to see code that looks like this. And when you see code that looks like this, I want you to know that they're calculating Bayes' theorem properly. Yes?
Basically, you're saying that they work out each of the numerators, store it in an array, and then the normalized function sums up.
Exactly. They work out, just to say what you said, work out each of the numerators, store it in an array, and when you call normalize it, it sums over all those, which is that. And then it divides everything by that sum. Whoa! So yes, exactly. You got it spot on, 100%. Yay. Hard concepts, one of the harder things that we'll do in this part of CS109. So you guys did all the hardest stuff. Now let's do some of the celebratory stuff. And some of the celebratory stuff is, now that you've mastered this hard concept in two variables, let's start expanding and just using your knowledge to be able to do more cool things. Learning goals for today. I want you guys to get some perspective on the art form of designing probabilistic models. And it is art as much as it is a science of how you generate models when there's many random variables. I'm going to teach you about this thing called correlations and covariances, and then I'm going to talk a little bit about independence in random variables. So we'll have a good conversation about key concepts while learning a new ability. Let's talk about how to make a model. There's two ways that you can represent a model. They're equivalent. Both of them describe the same thing. They describe how many random variables are random together. One way is to write a Python program. I'll get back to this later. You can write a model through Python, but it's easier to express it this way if you understand the mathematical way of expressing a model. And one of the most important ways of expressing a model is this thing called a Bayesian network, named after our most favorite mathematician, Reverend Thomas Bayes. And in a Bayesian network, you're going to express complicated graphical model, or complicated models of many random variables, and you'll draw them out, and then you'll give some probabilities, and this will specify the whole model. It's going to be great. I'll talk a little bit more about the joint distribution. But let's go back to our motivating example. Our motivating example, when we first started talking about probabilistic models, is WebMD. And as you recall, WebMD has this symptom checker. In the symptom checker, you can go and you list your symptoms, and then it tells you your probability of having different diseases. And so, wow, the HDMI is really slow here. So when you go through the symptom checker, it keeps track of a whole bunch of random variables. Some of those random variables are symptoms that you could have. So you have a whole bunch of symptoms, but you also have some random variables for causes, like actual diseases you could have. So there's random variables for, do you have diseases? There's random variables for whether or not you have symptoms. There's even random variables for things that they call, prior conditions that can make you more likely to have diseases. Like maybe your age, or I'm going to use undergraduate for now just for a good time. Maybe that could modulate probabilities as well. And you have all these probabilities, and they're working together. And if you want to do proper inference, if you want to tell somebody the probability of their fever, you have to be able to think about all these random variables together. The inference question is, I tell you an assignment to some random variables, and your job is update your belief in the other ones. Sometimes there's only one random variable that I care about you updating. So for example, I might tell you, I'm nauseous and I'm tired, and I want you to update your belief that I have the flu. So you observe some things and you update some belief. So here's one inference question. I can say, can you give me the probability that you have the flu, given that you're nauseous and you're tired? But that's not the only inference question. Oh, and you could use chain rule. You could use a couple of different approaches to solve this. I want to give you a sense that there's a lot of different inference questions. Like, for example, I could say, I have fever and sore throat, and I want you to update your belief that I have a cold. Oh, I also want you to update your belief that I am an undergraduate. Like any random variable, if I observe some, I should be able to update my belief in any other random variable if they're in a model together. So this is just that other question written in mathematical notation. So C0, I think, is for cold. Did I have another C? Yeah, chest pain. So C0 is cold equals 1. U equals 1, given that S equals 0 and fever equals 0. And again, you could use chain rule or you could use Bayes' theorem and start to approach this problem. So if you have all the joint distribution, my claim is that you could answer any of these inference problems. But I just want to make sure that we're on the same page about this. If there's 9 random variables and they're all binary, so they can take on 0 or 1, if you tried to represent this joint as a table, you just had a probability table which said, for any assignment of these random variables, I will tell you the probability. How big would that probability table have to be? Talk about with the person next to you, but also with the person next to you, see if you can come up with a question for what's confusing about this so that we can talk about it at this point. Talk about it with the person next to you. Let's come up with an answer. Okay. I want to talk about the answer. So that might not have been enough time. But hopefully, after a little bit of thought, you got 2 to the power of n. It's exponentially large in the number of random variables. If you have 1 random variable, you just need to store 2 probabilities. Well, actually, you can get away with 1 probability, which is just the probability of that random variable being 1. If you have 2 random variables, though, you end up with a grid. You have the 2 values that one random variable could be, the 2 values that the other random variable could be, and there's 4 values there. Technically, you could remove one of them because they sum up to 1. So it's still, 2 squared minus 1. If you have 3 random variables, it will be 2 to the cubed. I often don't think about this minus 1 because you could get away with not representing 1 random variable because they all sum to 1. But 2 to the 3 is normally how I represent if you have 3 random variables. And if you have n random variables, you're left with 2 to the n if you want to store it using a joint table. We learned about joint tables. It's clearly not going to cut it here.
Probably have like the negative 1.
Oh, yeah. So let's say you have, let's say you only have 1 random variable. And that random variable could take on the value of 0 or 1. So let's say I tell you the probability of 1 is 0.8. My claim is that there's always 1 value in your whole joint that you can just infer. So here I can know that this probability is going to be 0.2 because I can just infer it from that. It turns out if you had a grid, and let's make these numbers smaller, 0.6, 0.1. If I make this 0.2, this is 6, 7, 8, 9. I know that this one has to be a 0.1. So I could get away without 1. It's such a detail, but I'm glad you asked. But long story short, never in my life has this actually really changed anything. Because 2 to the power of n is so large, minus 1 is like, yeah, whatever. Good question. I wanted to motivate why we need models. If you want to be able to do something like this, if you want to write this web app, you couldn't do it using a joint probability table. You'd need a more sophisticated language for talking about how random variables can be random together. So shall we learn this more sophisticated language? Okay, yeah, n could be large. This more sophisticated language takes the name of Bayesian networks. And in Bayesian networks, you don't have to give the complete joint. you can leverage a hypothesis about how the world works to come up with a structure where you can express the joint with fewer probabilities. It's a beautiful thing. I'm going to tell you this story of a Bayesian network through a simpler WebMD. We'll call this the Vaden WebMD that's only got 4 random variables. There's fever and tired. I think of those as my symptoms. And flu isn't a symptom. Flu is a disease. You know how flu is different from fever? Flu maybe causes a fever. And undergraduate is just going to be like a pre-existing condition that might change the probability of seeing, some of these symptoms. That one. So the great idea about a Bayesian network is we're going to try and represent this without doing the exponential combination of all the probabilities. Now, if there's only 4 random variables, you might be able to get away with this exponential combination. You might be able to represent the 16, 2 to the 4 is equal 16, different assignments of all the 4 random variables jointly. But we want to learn a more sophisticated thing because when I go beyond 4 random variables, we know this is going to grow exponentially. So here's what a Stanford flu expert would do. They would try and describe the process of these random variables affecting each other using this thing called causality. Now, I think I said this lightly. I said flu causes fever. In the real world, we think that this random variable is the reason that this random variable would be 1 or 0. Even if it's not deterministic, it really changes the probability. Like knowing flu is really affecting fever, and we think of that as being the causal direction. If I tell you fever, that would change your belief that I have a flu. Like if I told you I have a fever, do you think I'm more likely to have a flu or not? Yeah, so it changes your belief, but I don't think it caused the flu. I don't think the fever is what made me have the flu. I think the flu made me have the fever. So probabilities go both ways, but causality we think goes in one direction. Do you guys buy this convention? I don't think it's that controversial to say that a flu causes a fever and that a fever doesn't cause a flu. Someone out there is like, but actually if you have a fever, you're more likely to get another condition at the same time. But like that's way too complicated. We're going with the simple version of the world. So what a Stanford flu expert would do if they wanted to try and represent this joint probability with many random variables in a more compressed way, is they'd try and describe causality. Flu causes these 2 symptoms. If you have a flu, that's why we think you might have a fever, and that's why we explain that you are tired. Similarly, we think that it's the undergrad nature which is causing you to be tired. And a flu expert would try and come up with a reasonable set of causalities that would explain how these random variables are causing one another. Now, the world is a complicated thing. There's lots of ways of telling this. Some people talk about like the butterfly effect, where everything is somehow connected. Like somehow being undergrad really might be the thing that's causing you to have a fever. Causality is a complicated thing. All causal models will be wrong in some way. But if you can generally get the structure of causality, you'll get a probabilistic model which is very close to correct and very, very usable. So step 1, describe the joint distribution using causality. Do you guys want to argue about my causality at all? I welcome arguments. We can have a debate about many of these things. Will's like, you definitely got that arrow backwards. Anyone want to? Yes.
Undergrads get the flu from dorms.
So you're saying undergraduate actually change, you're getting the flu from dorms, therefore it's the undergrad has a causal push to change whether or not you have a flu. I agree with that. I'm not going to model it. Yes?
Maybe like fever makes you more tired?
Yeah, fever is making you more tired. Now, I'm saying the flu causes the tiredness, but it might be that the flu causes the fever and the fever causes the tiredness. That's very reasonable. I'm not going to model it that way, but that's very reasonable. Yes?
Tiredness causes the flu because immune systems are not as strong when people.
I very much agree with this. If you're tired, your immune system goes down, and therefore we think of tiredness as causing the fever. These are all so valid. Now, if we got into it, I think we could argue for almost links between any 2 pairs of variables because there might be some way that every variable is causing one another. So our job isn't to get to all the details, it's to get the broad strokes of causality. And so even though all those arguments are right, these 3 arrows give us the broad strokes, and I'm going to give you a key. The more arrows you add, the more your probabilistic model will start to grow exponentially. If you have few arrows, you'll grow closer to linearly. And if you have lots of arrows, you'll start to grow exponentially. So I'm pretty reticent to add extra arrows. Such a good discussions. Yes?
Do you think you just go over the visualization again of the joint distribution before you move on?
You mean of this one?
Yes.
So in this visualization, every circle is a random variable. And here I'm using lines to say that I'm hypothesizing that this random variable is causing this one's value. Oh, we're going to tell, I haven't told you how to express a joint using this yet. I've just gotten you halfway through there. We got in step 1, but if you know step 2 and 3, we'll know how to express the joint. But you're right, that's your problem right now. It's like, I've told you this beautiful picture drawing technique. I have not told you how to represent a joint, which is what you need.
Or less accurate if you draw like every single combination of arrows possible?
Oh, that is a deep question. If you could estimate every probability perfectly, it would get more accurate. But the more arrows I draw, the harder it will be for you to estimate the many more probabilities you have to estimate. And because of that, it might get worse. So it's actually a complicated answer. And often, that's kind of how you choose. You might keep adding arrows until your accuracy starts to degrade. There will be a peak point. There's a whole conversation about overfitting and underfitting, which we can get into in 221, but that's the broad strokes of the conversation. Yeah, this is so cool. I'm so honored to be able to show you Bayesian networks for the first time, because it's, I think, one of the cooler pieces of technologies. In fact, the people who worked on Bayesian networks have won all the math awards and all the big CS Turing awards, because this combination of mathematics and computer science was just explosive for the sorts of problems we could solve. Now, I have told you how to draw a pretty picture. I haven't told you how to define a joint. If you want to define a joint using a Bayesian network, here's your next task. Once you've got all your arrows, for every single random variable, I want to give you the probability of the values it can take on, given the assignment to all of its immediate parents. So I've redrawn our Bayesian network over here. When I say give me all the probabilities given its parents, let's start with these two lovely nodes up here. They have no parents in this graph. I mean parents by the graphical term parents, right? There's no nodes that have arrows pointing into it. Therefore, when I say give me the probability of this node given its parents, I just mean give me the probability of this node not conditioned on anything. And I can tell you the probability of a random person having a flu is 0.1. That's your job. This node also doesn't have causal parents. So if you want to specify, give me the probability of this random variable taking on the value 1, but not conditioned on its values of its parents, because there's no parents here. So what's the probability of somebody's an undergrad walking into Vaden? And Vaden says 80% of the people we see are undergrads. Yes? Yeah, these are, I like to think of these ones at the top, they look a lot like priors. But they're all going to be probabilities. And yeah, actually you can think of this as like, we're going to describe the joint, and you can kind of think about that describing your prior belief. And then when you observe things like I observe it's an undergrad, I observe their fever, then all your probabilities will change, and that will give you a posterior. So yes, let's call that a prior. So these two, do you guys make sense? If I tell you you have to provide the probability of them giving your parents, these ones are pretty straightforward. This one's a little harder because it's got a causal parent. I have to give the probability of this random variable given its parents. So I have to say, what's the probability that fever equals 1 given flu equals 0? So I have to say, if flu is 0, what's the chance of having a fever? I also have to say, if flu is 1, what's the chance of having a fever? Now, notice I say for all the possible assignments to the parents, and for each of them, I just do the probability fever equals 1. I might care about the probability that fever equals 0. How could I calculate the probability fever equals 0 if I know the probability fever equals 1? You guys feel it in your bones. I hear it murmuring in the air. Just 1 minus this. You don't have to specify fever equals 0, because if you specify fever equals 1, then if you tell me flu equals 0, I can know probably fever equals 0 by just doing 1 minus this. How many parents does fever have? Just 1. All the assignments to the parents are assigning 0 to the parent and assigning 1 to a parent. I have given you the probability of this random variable given all possible assignments to its parents. Oh, I haven't actually put numbers here, but I'd have to, I don't want to get these different from what I have on the slides, so I'll add those in a second.
Right now we're sort of representing fever as a Bernoulli. I mean, either you have a fever or not. I mean, in the case that you want to sort of track all the ranges of fever, would this be scary?
I intentionally made everything a Bernoulli to start with. You are right that we are absolutely going to be able to expand this model so that fever could be something like low, medium, high, or even it could be a real valued number. There's lots of ways we can do this. In fact, in the elephant example, we had a Bayesian network, but the thing over here was weight, which was continuous. So it's totally possible to represent something that's not Bernoulli, but let's start with Bernoulli, just because we're doing a whole bunch of random variables, and that's a nice place to start. Good question. Okay, so I'd have to give you two numbers here. So 0. What's the probability that you have a fever given you don't have the flu? Oh, that's very low. And if you do have the flu, you might have a fever, but you might not. Let's say there's like a 70% chance that you have a fever. Yeah, question.
Is this the most sophisticated model of its like space complexity Bayesian networks?
Sorry?
If we're trying to model n random variables,
Yeah.
is the Bayesian network going to be the best model with whatever space complexity?
Yeah. So you can imagine like how much space do you have for representing your probabilities? I think Bayesian network is one of the best ways I've ever seen for representing a joint efficiently. It's like the most compressed you could get. That really comes down to if you are smart about your causality though. Like as I said, if you drew arrows between everything, a Bayesian network will degrade to a joint probability table. Okay, so here I've given the probability this random variable and this random variable and this random variable given all their parents, but I haven't given the probability this random variable given all the assignments to its parents. It has two parents. Both of those parents can take on two values, and therefore I have to give four numbers. The probability of being tired given in all these four cases of assignments to its parents. Do you guys see how more arrows can make things exponential? If this had 3 parents, you would have 2 to the 3rd. If this had 4 parents, you'd have 2 to the 4th things in this table. So to specify a Bayesian network, you first draw your arrows, and then for every node, you give the probability of the node given its parents. Wildness, coolness, powerful. You're going to use this to do some neat things. Yes?
Probability with Bayes theorem.
Oh yeah, you can calculate the probability in lots of ways. You can use Bayes' theorem, you can use the chain rule, lots of good ways you can calculate probabilities. We'll go over that in a second. Okay, maybe I'm building you guys up too slowly because you guys are getting ahead of me. We can talk about this implicit assumption. Now, we've defined every random variable as the probability of itself given its parents. So I'm just writing on the slides what you've got on the board here. I do want to note that when you are making a Bayes net, when you write these causalities, you're doing something very sophisticated that you don't need to understand, but if you did, maybe that would be cool. The sophisticated thing that you're doing is you're starting to talk about independencies just by drawing arrows. It turns out that if this is the causal structure, flu does not change your belief in undergraduate. It tells me that if you change your belief in flu, like if I tell you have a flu, my belief that you're an undergraduate will not change. And these sets of arrows are telling me that undergraduate's independent of flu. Now, as I said, I'm going to leave it to a later class for you guys to do the complicated math of figuring out exactly what are all the independencies assumptions that are coming from the arrows, but I want to explain where the compression is coming from. The compression that you're going to get of being able to describe the joint in a lot fewer numbers is because there's implicit independencies that you get from causality. Basically, by saying flu doesn't cause undergrad and undergrad doesn't cause flu, you are going to gain some independence, and that allows you to express things more compactly. One thing must be acyclic. You can't have undergrad cause tired and tired cause undergrad. It will completely break your whole model. If you keep to that rule, then you're just fine. Okay. Now, my claim to you is this. The Bayesian network has this cool assumption. If you give me all of these things, I can reconstruct the joint. The way I can reconstruct the joint, it says, instead of representing the joint as this whole honk in probability, you don't even have to do chain rule. Like if you wanted to try and calculate this, maybe you could represent it just from a joint table, or you could have chain rule try and calculate it. Bayes' theorem says every time you get a random variable, if you're trying to get a joint, you just multiply that random variable's value given its parents. What a crazy thing. I think, though, this makes more sense when I show you a Bayesian random variable expressed through code. Can I show you that? Do you guys want to see a joint distribution of a Bayesian network? This one expressed in Python? Yeah. Oh man, Python's such an expressive thing. So much more expressive than slides can be sometimes. WebMD. Okay. I have my Bayesian network, and it's expressed as a code. And particularly, if you can write code that can draw a sample from the joint distribution. And by draw a sample, I mean like when I run this program, it starts making fake students who either have the flu, or undergraduates have a fever, or are tired. If you can write a program that can sample from the full joint assignment, so you're giving a value for every single random variable together jointly, that is an expression of the joint distribution. For a Bayesian network, I'm going to start at the top, and I'm going to sample each random variable, and then if I get deeper in, I'm going to use the values of its parents to update my belief of the future ones. May I? Okay. So, first of all, we've got to start with flu and undergraduate. Those don't have parents. So when I sample them, I'm just going to sample from Bernoulli. Bern is a function that I wrote that just either returns a 1 or a 0. This returns a 1 or a 0 with a probability of 0.8, and this returns a 1 or a 0 with a probability of 0.1. So after I call these two functions, I've decided, does my current fake person have the flu, and is my current fake person an undergraduate? After that, I need to choose fever. But when I choose fever, I'm going to follow the Bayes theorem idea. And when I choose fever, its probability will be based on the probability of its parent, or the value of its parents. So I've chosen flu. And if flu was chosen to be 1, then they have a high chance of having a fever. If flu is chosen to be 0, then they have a low chance of having a fever. So at this point, I've expressed a joint between these 3 random variables, and I just need to be able to simulate this last one. And then when I simulate it, then I've pulled one sample from the joint probability. When I choose tired, it's more complicated because it depends on my previous choices for undergraduate and flu. And there's 4 different combinations for undergraduate and flu. And in each of those 4 different combinations, I could have a different probability of whether or not somebody's tired. They don't have to add up to 1. For example, maybe it's guaranteed you're tired if you're an undergraduate with the flu. And you can still have positive probabilities, and they don't add up to 1, and that's fine. Now, at this point, I've chosen all my variables. And as such, I've pulled from the joint. And the claim of the Bayesian network is that this is equivalent to if you had a joint probability table and you were pulling from a joint using a lookup into the joint probability table. That was a lot, so yes, let's talk about it. Question?
Can you just explain what exactly is happening when you say choose fever based on?
I'm sampling. So when I say choose fever, I'm going to end up with 4 variables every time I make a fake person. They're going to have flu, undergraduate, fever, tired. They're all Bernoullis. They'll all be 0s or 1s. So when I say choose flu, I mean for this particular sample, for this particular person who I'm making a joint pull from their probability of the joint distribution, I have to decide if they have the fever. No, this is like making a fake person. And some fake people will have fevers and some fake people won't. So this is not inference. You've got no information about a person. So this is a good thing to talk about. I'm glad you asked. When you're actually at Vaden and somebody walks in, they will tell you some things. They'll say, I have a fever and I'm an undergraduate. That's an inference question. And in order to solve the inference question, we need a different thing called a joint. And the joint just says what's the probability of a complete assignment to the random variable. So there are 2 things to keep separate. The inference task of somebody's just walked in and they've told you they have a fever, and they've told you they're an undergrad. That's a separate thing from expressing what's the probability of these 4 random variables taking on any possible assignment. And you need this one to solve this one. We need the joint if we want to be able to solve the question of if somebody has a fever and they're an undergrad, what's the probability they've got the flu? Such a good question. So what I've got here is not doing inference. It is sampling from the joint. That leads to more questions, yes?
Is there something you have to do to calculate the Bernoulli values for tire, or are those given to you?
I actually couldn't hear you. It was a little too quiet.
Is there something you have to do to calculate like the 1, 0.8, 0.9, 0.1, like the Bernoulli values for tire?
Oh, for tire, like how do people come up with those numbers? Is that what you're wondering?
Yeah, like did you get those numbers, or did we have to calculate them?
So this is such a great question. Anytime we've got probabilistic models, there will be numbers, and there's a great question of where do those numbers come from? For example, where do these numbers come from? The answer is I made those up based on a reasonable assumption. And that's one of the places that probabilities can come from. Maybe an expert gives you a pretty reasonable guess. A different way that you can get those numbers is from data. You could say, I've collected data on all the people who've come into Vaden and 8% on undergrads. I've collected data on all the people who've come into Vaden, and if I look at all the people who didn't have the flu and were undergraduates, I can calculate what percentage were tired. So you can calculate from data, or sometimes experts make them up. And that happens all the time, and you should be wary of them, cheeky experts. Yes?
So the tired note that's a joint table, right?
Sorry?
Is that a joint table?
I couldn't hear.
Is it a joint table?
It's like a conditional table. It's like conditioned on each of these values, I'm going to tell you the probability of tired. But it has a lot in common with a joint table. So, if the parents have these values, then what's the probability of tired? So conditional, but very similar. Yes, one more.
Just to clarify, what exactly does the Bernoulli function do? Why do you say like it's Bernoulli this and not just
Bernoulli returns one of two values, 0 or 1, and it returns a 1 with the provided parameter. So when you call Bernoulli, this will give you back either a 0 or 1, and the chance of getting a 1 is 0.1. And when you run this function, when you run this, hey, wait, that's not what I wanted at all. Python sample. Now, this is such a programmer's answer to how to express a joint. I've got a joint if I can pull a whole human with assignment to all those 4 values, and the assignment must be corresponding to the real likelihood of somebody having this particular assignment. Like the chance that I get not tired, not fever, not undergrad, and not flu should correspond to how likely that particular assignment is. And the Bayes net argument is that because I built a Bayes net, and because I took each variable given its parents, that this is the proper joint distribution. It is implicitly making some independent assumptions. Because causality is not perfect here, they will be wrong, but this is going to be so useful. So this is a wrong model, but allow us to go from exponential space to express a probabilistic model to linear space to represent a probabilistic model. So even though it's going to be a little bit wrong, this is going to be such a good way of representing a joint. Boy, have I said some complicated things. But the real complicated thing I've said here is that I told you how to make a Bayes net. It's simple. Draw your causality, give the probability of every random variable given its parents. And then my next claim is that if you multiply the probability of every child given its parents, you get the joint. And or if you do a sample where you sample from the parents and then you sample from the children given the parents, you get a sample from the joint. And that's really the Bayes theorem assumption. Bayes nets tell what we call a generative story. They say, if you have a person with an assignment to all these 4 random variables, here's this generative way that you got that. You started with these random variables, and then you generated the children based on the assignments to the parents. I really feel if you could choose one thing to focus on if you find this confusing, I really do think the generative story of the code is really important. It's saying, this is how I think the world works. I think if you were to generate a random person in this world, you would generate it in this way. And that's why I call it a generative model. We generate the parents, then we generate the children conditioned on the parents. And the generative model also has the probabilities of every random variable given its parents. Wow, so much. Okay. Are you guys ready for this? I have told you a lot of important things. I've told you about this beautiful way of expressing a joint. But that is basically useless if you can't do the cool task of inference. And the cool task of inference says, I want to change my belief given that I've seen some evidence. We're going to get to inference. Don't you want to get to inference? Because then it's like, then the whole modeling was worth it. In order to get to inference, I first want you to be able to solve this task. This is a joint assignment. It's a probability, but I'm asking for a particular assignment to all 4 of my random variables. And I have a tricky task that's going to check your understanding. Can you tell me the probability of this particular joint assignment? If you're stuck, think about the generative story. What is the probability that the person doesn't have a flu, they are an undergraduate, they don't have a fever, and they are tired? Can you figure out that probability? And this will be the first step towards that beautiful, beautiful dream that we can do inference on any graphical model. Okay, talk about it with the person next to you. Let's see if we can figure out how to do this. Ask me lots of questions. I love this conversation. Okay. Oh. Okay. This is some heavy math, but this is the hardest conceptual part before we get to inference. So I do want to slow down, and I want to answer any questions you may have. So the Bayesian net assumption says that if you want that whole joint, you just take the probability of every random variable, but if that random variable has causal parents, you have to write it conditioned on the value of its causal parents. It's a generative story. It's like, first, we figure out if somebody's an undergraduate. What's the probability somebody's an undergraduate? Yeah, you guys are going to help me out because I can't see the screen, so just yell it out so give me a chance. What's the probability somebody has a flu?
0.9.
Yeah, what's the probability they don't have a flu? Ah, okay, so this one's 0.9. So the chance that somebody's an undergraduate and they don't have a flu, Bayes' net is saying the chance that these two things multiply by each other. That's what independence looks like, you know. The probability of this particular assignment being equal to the probability of each of them on their own. That's independence. Now, how about this one? The probability that fever is equal to 0 given that flu equals 0. So what's the probability fever equals 1 given that flu equals 0? Okay, and then what's the probability that equals 0? Ah, fantastic. Because it's just going to be 1 minus the probability that fever equals 1. Now, if undergrad equals 1 and flu equals 0, what's the probability that tired equals 1? 0.8. Okay, good. I was about to have to look at my computer. The claim is that this joint distribution you can get by just multiplying these 4 probabilities together. And this is saying, you know, this is the chance that you see all of these particular 4 random variables at the same time. No matter which assignment to random variables I gave you, you could continue to use the generative story, and you can get a probability of assignment to all the 4 random variables jointly. Question?
Did you know there's a probability that fever is equal to 0 given that flu is 0 again?
Okay, so let's look at fever's node. Oh wait, did I get this wrong? Oh yeah, totally. I didn't look at the screen. Okay, if flu is equal to 0, the probability you have a fever is 0.05. If you don't have the flu, the chance you have a fever is very, very low. So what's the probability that if you don't have the flu, that you don't have a fever? 0.95. I misheard you guys. I heard 0.5. And so this should have been 1 minus 0.05. Yeah?
So a probability table, the size of it is 2 to the 4th, right?
Yes.
So what would it be as like a net?
So let's look. 1, 2, 3, 4, 5, 6, 7, 8. We represented it with 8 numbers instead of 16 numbers. It sounds like you've saved half the numbers, but it's better than that. You've gone from exponential to linear. So if there is more than 4 random variables, you go from like 1 billion values in your joint table to maybe like 100 probabilities.
The number of arrows?
It's based on the number of arrows. It's based on, if you think of the child with the most arrows, that's the one that's really going to define it because it will have 2 to the power of how many parents it has, the child with the most arrows. Yes, another question.
How do you break down the table to make that choice?
How did I break down the table?
Line to make the list.
I started with the causal story. I started with the nodes with the least parents, and I took the probability of them, given their non-existent parents, and then I went down from the nodes with the least parents to the nodes with the most parents. So the parent nodes to the children nodes. Yeah, question.
Explain again how you calculate the probability of being tired just because like it has 2 parents.
Yeah, so the Bayes net idea is that we're saying tired is caused by flu in undergrad. So that's what I need to know if I want to figure out somebody's tired. And if you tell me that flu is 0 but undergraduate's 1, so flu is 0 but undergraduate's 1. So if that's the assignment to its parents, the chance that you're tired is 80%. Because even though you don't have a flu, you're an undergraduate. That makes us sleepy. And so that's the idea. So the Bayes net is not taking into account whether or not you have a fever. So there's all these things that is not taking into account that would have implicitly been in the joint table. We're representing it in a much more compressed fashion.
So we can take those as given because we know that we're calculating the probability of all of those 4 things being true at the same time.
Exactly.
Okay.
It's the idea of the Bayes net is, the big assumption is saying that the joint is equal to the product of all these probabilities. And you can think of that as the Bayes net assumption. It's true if the causality is perfect, even though the causality is not always perfect.
We have to be given a lot of these probabilities up front, because like it doesn't seem like there's a way to get them from the base net.
Oh, you mean like someone has to give you these numbers?
Yeah.
Yes, absolutely. And they come from 1 of 2 places, experts or data. You could use data to estimate them. By the way, if you have to estimate 2 to the n numbers, that's hard. If you have to estimate like O of n numbers, that's a lot easier from a data set. So you could use a data set and you could have filled in these numbers for me. Yeah.
So to clarify, using this Bayesian strategy, we only have to have like 4 terms. In the other example, we use a general like joint probability table. We'd have to have 16 terms. What would those terms look like?
You would have a cell in your table for every assignment. You'd have a cell in the table for this. And you have a cell in the table for like, if you flip this to a 0, for any binary combination of the random variables, you would have a cell in your table. That's why it's such a disaster. A total disaster.
So would you say that we've reduced the number of things because we've cut down the possibilities by making causalities?
Yeah. Causalities implicitly imply independencies. You don't have to know exactly which ones, but that's why we're getting such reduction. Okay, one more question, then I do need to continue the conversation.
Causality implies independence. That's why we're using like the and, like the rule of and.
Yeah. And actually, the joint is and. The joint says what's the probability of this assignment to this random variable and this one to this other one and this one together. That's what the joint's all about. And that's the thing you would need to solve any probability question. And speaking of which, I'm going to bump this up a notch for you guys. Oh, man. Assume you have, for any assignment, you have a way to calculate the joint. You now have the joint. My claim is you can calculate any conditional probability. Are you guys ready? What I really want to know is the inference problem. The joint is just like scholastic. Inference is real. It solves people's problems. I want to know the chance that I have a flu. So what's the probability that I have the flu? Given I am not an undergraduate. I am in fact much older, though I might look charmingly young. I am in fact a father. So I am an undergraduate. I am not an undergrad. Am I tired? No, I'm actually feeling kind of bouncy. Wait, tired equals 0. And I don't have a fever. So this should be pretty low, but inference would allow us to answer any question. And my claim for you was, no matter what question you have, if you have a joint, you can answer it. May I just explain why? Let's first look at this using the definition of conditional probability. If you use the definition of conditional probability, it would say that this is equal to flu equals 1. My L's are also a disaster, just like joint probability tables. Doesn't that L look just like my E? Ah, L. Whatever. No, I can't use a capital as a subscript. It feels wrong. Ah. Maybe I do fever. Whatever. That's not important. So, definition of conditional probability says it's the probability of all these things together divided by the probability of the thing on the right-hand side. Do you remember when we first learned conditional probability? Who would have known we would take it to the max like this? That's an E. So this is the definition of conditional probability. Luckily for us, this thing is a joint. Could you calculate this probability? You could use exactly the same method to get a joint. Could you use exactly the same method to get this term? No, because this term doesn't have flu. But there is a tricky little idea that you guys might have in your head that would allow you to get this term where flu isn't existent. And my key idea for you guys is I say, think about two cases. The case where all these things are true and somebody has the flu, and the case where all these things are true and the person doesn't have the flu. How could you get this one using joint assignments? No, I want you guys to, let's meditate for a moment. Silence. Find your calm. But not your sleepy calm. You're like mindful calm. Okay. Does anyone see a way we could do this? And I'm looking for somebody. Yeah, somebody hasn't spoken today. Yep.
On when flu equals 1, and then sum that with the event condition when flu equals.
Yes, there's an even easier version of the law of total probability that we can use. So there's two versions of the law of total probability, one that's got the condition and one that's got the and. And the law of total probability that has the and looks like this. I'm going to try and write this without a sum notation, though my heart really wants to use sum notation. I just think it's going to be easier. I'm going to call this whole thing on the denominator happy symbol, because I don't feel like writing it again. Are you guys okay with that? So we've got ourselves our happy symbol divided by, and we want to get an expression for this. And I'm going to call this whole set of equations my unhappy. I don't know why it's unhappy. It's really unhappy, but I'm just going to do that because I don't want to write it again. So it's the probability that flu equals 1 and all those other random variables plus the probability that flu equals 0 and all those other random variables. So all those three unhappy, all those ones are smiley face. So this is the probably smiley face. Oh my God, what an emoji answer. I feel like the most millennial person right now. So the law of total probability has two versions. You can say that if you want to get this thing, there's a background process of whether or not somebody has flu. And the probability of this is, the chance of that assignment in both the cases where somebody has the flu and somebody doesn't have the flu. And if you add up those two mutually exclusive cases, you will get the probability that somebody just has this assignment of random variables. And now an interesting thing has happened. We have ended up with joint assignments. In this expression, I've got a value for every random variable. In this expression, I've got a value for every random variable, in which case I can use this process to get them. There's a fancy term for this. It's called marginalization. Marginalization was easy to think about when we get two random variables. When we get to more random variables, it gets a little bit harder. But marginalization says, if you want the probability, if I want to write this out the way I would have liked to using some notation without smiley faces, I would have said that this is equal to the probability that u equals 0, t equals 0, and fever equals 0 is equal to the sum over all the assignments to flu, the probability that flu equals the current thing in my for loop and all of these things. So u equals 0, tired equals 0, fever equals 0. And those are two different poles from the joint distribution. Because of marginalization, everything can be solved as a computation starting from the joint. If somebody gives you the joint, you can calculate your numerator and your denominator of any inference task. Whew, that was a lot. Okay, so what have we talked about? First, I presented a problem. You want to represent many random variables, but you can't using a joint probability table. You want to be able to do inference, but you need a joint, but the joint probability table is not working. Then we gave you Bayesian networks. It's a very compressed way of representing a joint, and once you have Bayesian networks, because you have a way of representing the joint, anytime you have a conditional probability, you can solve it by starting with the joint and marginalizing out all the things that you need to. And there you have it. We have a full story. We now have Bayesian networks, and they're useful for solving any probability question. Oh. Let's take a pedagogical pause. If people have questions, come, you can ask me, but let's take 2 minutes because that was a whole bunch to cover. Yeah. Why don't you come up to the front?
Why is it called a Bayesian network if it's not doesn't?
Independence in random variables. We have known independence for a long time. If I told you 2 events were independent, oh, do you guys remember the day of events? Ah, so humble. It was like the Shire before we went on our big adventure. Events. Okay, but in events world, if you want to claim that 2 events were independent, you could show it mathematically. You could say that the probability of the 2 events happening together is equal to the probability of one event times the probability of the other event. And that was really the definition of independence, though there was an equivalent version of chain rule. If 2 events are not independent, they're called dependent. And intuitively, aside from all the mathematics, if you tell me that one event's independent of another, it doesn't give you information. In the world of random variables, the exact same logic holds, because as we know, an assignment to a random variable is an event. That's an event, and that's an event, so independence is going to look exactly the same. But the one increase in terminology is that if you claim two random variables are independent, then this equation has to hold for any chosen assignment to values. So whatever you choose for little x and whatever you choose for little y, this equation must hold if the random variables are independent. So it's a much stronger claim. It's saying knowing anything about this random variable will tell you nothing about this other random variable. It's a much deeper claim, but at the end of the day, it's the exact same equation that we've known, lived, and loved already. So let's go back to our wonderful friends, after all this time, still so good to us, dice. Let's say you have dice 1 and dice 2 are the outcome of two rolls, and S is the sum. So the first question I could ask you is, are events that the dice 1 equals 1 and the sum of two dice equals 7 independent? Now, we looked at this earlier, and if you figure out, what's the probability that the first dice equals 1? Well, that's 1 over 6. What's the probability that the sum of two dice equals 7? Well, it turns out there's 6 ways that you can make that happen out of 36, so that's 1 over 6. And what's the probability that the first dice is 1 and the sum is 7? Well, that means that the first dice was 1, second dice was 6, and there's 1 over 36 ways of doing that. We did this earlier in class. Here's another event that we looked at in class. We said, if I tell you the first dice is 1 and the sum is 5, are those two events independent? And the answer was no. If I told you the first dice was 1, it changes your belief that the sum will be 5. Because if I told you the first dice was 6, you know the sum can't be 5, for example. So if I tell you the first dice is 1, all of a sudden you think, okay, it's more likely that maybe the two dice add up to 5. 7's the weirdest number. Like, why is this independent? Why is knowing the value of the first dice independent of the sum being 7? And that's this question. And it turns out it is independent. No matter, so basically these random variables are not independent, but this first dice being 1 and S being 7, the reason it's independent is if you care about knowing if your sum is 7, no matter what you get on the first dice, there's exactly one thing on the second dice that leads to the 2 being 7. Anyways, since this is true and this is not true, it's not true that the two random variables are independent. For the two random variables to be independent, all of these questions would have to be check marks for any assignment to D1 and S. Stronger claim, as I said. Okay, and this might lead to the next question. And this is something we'll do if we just have a little bit of time. But what if you cared about discovering causality just from data? So right now we have this idea of probabilistic models. We have a way to do inference if you have probabilistic models. What you don't really have is where do those probabilities come from and how could I design the probability network myself? Do you guys want to learn that? Okay. What I have for you is a challenge. I have all this data of all these kids in the UK and they're rating 1 to 5 whether or not they like all these different genres. And there's like 30 different genres. So you could imagine a probabilistic model of 30 different types of music all together. And we could go and make a Bayes net. We definitely need something like a Bayes net because 2 to the 30 is too large if you want to talk about joint probabilities. So if you want to say something like, what's the probability somebody likes folk given they like classical, any general inference, we'd need a joint. So we've talked about finding independencies before in class. When we had the bat DNA problem, we had data like this, and we could search for independencies. And independencies are going to give you some hints as to how you want to draw your causality. Because if it tells you, like if you get your data and it says flu is independent of undergraduate, then great, maybe you start to make both of those your parents. The bat data problem we did, you guys could figure out independencies. But I have a different question for you. What if they weren't Booleans? What if they were continuous numbers? How could you find independencies of random variables that take on not just true or false values? So how do you find independencies in random variables, not just independencies in events? The bats were events. Now I've bumped this up to random variables. And it really starts with this question. Here is a picture of two random variables that look independent. And here's a picture of two random variables that are very much not independent. And my question is, what are you curious about? What do you wonder? And what do you notice about these two different pictures? Yeah, I mean, this one looks kind of splotchy. And this one kind of is like, looks a little bit like this diagonally thing. That feels good, yeah? Yeah, if I told you, the x value of a number here, you could kind of have a function that could take that x value and give you a guess for the y value. Whereas if I tell you the x value here, you're like, I don't know what your y value is. Your x value really doesn't tell me that much about what y value I predict. And that's really the idea. Like in this picture, these things look quite independent. One random variable is not telling you about the other one. And this one random variable is very much telling you about another one. Now, how about this one? Looks kind of like the same picture, but I've shifted things. But my question is, semantically, is the same story true? Here, if I told you about the x value, one value of one random variable, could you predict the other one? Pretty well. Yeah, you definitely update your belief. If I told you the x value here, would you update your belief on the y? Doesn't matter that I shifted it. It's the same thing. These ones look quite independent, and that one looks like there's a little bit more of a relationship. There is a numerical quantification for how much two random variables vary together. It's like a beautiful dance. You imagine you have two random variables, and when one goes one way, does the other one also go the same way? And when one goes a different direction, does the other one follow it? This measure of whether or not two random variables vary together looks like this. If you take any point, you can say, how far is this point deviating from the x's expectation, and how far is it deviating from the y's expectation? And you can product those two things together. And if you product those two things together, it has this wonderful property that if the 2 points are deviating in the same direction, then you'll get a positive number. Like if they're both negative, if x is below its mean and y is below its mean, then you'll get a negative number times a negative number, and that will give you a positive number. And people have decided that this is a really good way of calculating numerically a simple statistic to say, are my two random variables being random together? Is one of them telling me some information about the other? Now, if you took other points, like this point close to the middle, if you calculate this term, it would be close to 0. And if you take this point down here, if you calculate this term, again, it would be positive because the x minus its expectation is negative and the y minus its expectation is negative. This term, if you calculate in expectation over your two random variables, gives you something that you might have heard of before called the covariance. And the covariance says that if I find points where both of them are deviating from their mean in the same direction, then it'll give me some positive product. And if I find points where things are deviating in negative directions, it'll give me a negative product. If you took all those positive negatives and averaged it for this plot, you get something close to a 0. There's some positives, there's some negatives, but they generally cancel out. But if you take something, I want another picture. Okay, well, if you took a plot and it just had points on this diagonal, then all the points would either be contributing positive values or 0. So in expectation, you would get something positive. And in fact, if you take a point and x and y are both above their mean, you get a positive number. If x and y are both below the mean, you get a positive number. But if they differ, like if one's above the mean, the other one's below the mean, you get a negative number. The covariance is the expectation of all these products over the whole random variables. And if you calculate this, then you would get what we call the covariance. It's a measure of how much two random variables vary together. Now that covariance expression is hard to calculate. It turns out it's numerically equal to this. There is a whole derivation of that, which you can check out in your own time. I wanted to include it here for completeness. But I wanted to give you a sense of how you would calculate this. The way you would calculate this is, the covariance formula at the end of the day, you could write it like that, or you can write it as this expression. This is how we often calculate it. It turns out this measure of how much these two things vary together is the expectation of the product minus the expectation of each random variable multiplied together. So if we took this data, we can calculate the expectation of one random variable. We can calculate the expectation of the other random variable, and then we can calculate the expectation of the product. To calculate the expectation of the product, we just take the products over all the points and calculate its average. And if you did this, you would get a way of calculating the covariance. What I'd like to show you now is what it looks like if you look at the covariance of all of those bats. Sorry, not the bats, the music. This is the covariance for all of the different music tastes that I told you I wanted to challenge you to model. If you look at somebody who likes punk, it has a very high covariance with rock. If you look like somebody who likes metal, that also has a very high covariance with rock. But it turns out, like if you look at metal or hard rock, it has a very negative covariance with pop. So if you tell me somebody is very positive on the metal scale, I think they're more likely to be negative on the pop scale. It's a simple statistic. It's not telling you a complete causal story, but it's giving you a sense of which random variables are varying together. My clue for you is, this is a little bit beyond 109, but if you want to come up with causality from data, this is the first step. You take all your random variables and you look at how much they covary. And from this covariance, you try and find structures and you try and have the art form of designing how you think the world works. It is an art form, but it will lead to something that is representable by a computer, a Bayesian network. What a beautiful thing. That was so cool. You guys asked such amazing questions. I'm really appreciating you guys. Thank you for all the hard work you do. Come back on Friday. We'll continue this conversation and learn rejection sampling. Thank you guys and see you guys later.